It is my distinct pleasure to introduce our esteemed keynote speaker for today, Professor Gašper Beguš, who currently serves as an assistant professor at the Department of Linguistics at UC Berkeley and is affiliated with the Institute of Cognitive and Brain Sciences. He earned his PhD from Harvard, and after that he served as an assistant professor at the University of Washington before joining the distinguished faculty at UC Berkeley. His research is at the forefront of linguistics, focusing on the development of deep learning models for speech data and exploration of well-understood dependencies in speech and interpret internal representations in deep neural networks. Moreover, Professor Beguš serves as the lead linguistic for the CETIS project, an initiative at the cutting edge of machine learning. The latest research from CETIS explores the application of machine learning to advance our understanding of non-human communication, particularly focusing on the communication of sperm whales. So, in a world where technology and linguistics converge, Professor Beguš stands as a pioneer contributing to the intersection of deep learning, linguistics, and animal communication. So please join me in extending a warm welcome to Professor Gašper Beguš as he shares insights from his groundbreaking research and the fascinating world of machine learning in linguistics.
Thank you so much for this very nice introduction. So today I want to talk about AI interpretability and how it can help us gain novel insights into various data types. Okay, so the title of the talk, New Insights into Unknown Data with AI Interpretability. So we understand the world pretty well around us, but there are many things still to be discovered. And it is an exciting time because for the first time, we have a non-human intelligence that is good enough that can help us gain insights. But how can that happen? So we humans are biased, right? We see things that are important to us. And that can sometimes prevent us from observing all patterns in data that are meaningful. So understanding AI is really the next frontier in AI research. AI, we've learned today and in other cases, is really good at performing well on many tasks. It can produce conversations, it can generate image like this one. That are really good, and that was not possible even a couple of years ago. But we don't understand how AI is doing that. We don't understand its inner workings. And so the important thing is that if we understand inside these networks how they're producing data and how they're organizing their representations internally, that can really help us bring new insights that we as humans might not have. And that is true for any data type. Today I'm going to talk about whales, but this general approach of pairing performance of AI with internal understanding of AI has the potential to really bring insights into various data types, including financial data or protein design or geometry, or drug discovery. So it is really kind of all-purpose precisely because these models are built to be all-purpose. Now, how did we go about this? We want to discover what is meaningful in one of the most exciting data that I've had the pleasure to work with, which is the sperm whale communication system. Sperm whales we'll talk a lot about them. They have a really fascinating communication system, but we don't know almost anything about that. And I'm gonna give you showcase a story of how we used AI, generative AI, together with interpretability techniques, and really got a suggestion, the model itself pointed us into one direction, and we found this really exciting property about this communication system that was unknown before, but predicted by our models and our interpretability technique. So how do we do that? We talked a lot about large language models, and they're great, but they don't learn like humans. And it is important to build both models that don't learn like humans and models that do learn like humans. Why is it important to build models that learn like humans? Because we understand them well. So no baby learns from text. And in our lab, we're trying to build models that learn more like humans. So instead of having our models learn from text, we have our models learn from raw speech, which is more human-like. And again, this is crucial because we understand pretty well how humans learn, and we have very poor understanding of how these models learn. And making them learn more like humans can be really helpful in this respect. So how do humans learn language, right? Or what even is language? So this is an old image for how we conceptualize language learning in the linguistic science or cognitive science. So first, I have some information in my brain, right? And I learn to move my muscles that move my articulators, my tongue and mouth, so that I encode my information into spoken language, into sound. And that sound travels in the air or via Zoom into your ears, and you hear it, and then you decode that information, right? And human babies have to learn this pretty complex process of coming up with an information, encoding it into sound, and then decoding it from raw sound. And there's no explicit instructions when they learn this, right? So they learn this by just listening to sounds of language by their parents or caregivers or the environment. And this is a model that we're building. This is probably the closest approximation of human language learning that we were able to build with deep neural networks. So our models learn to move mouths so that the sound that they're producing approximates the sound that they're hearing and also has a meaning, okay? So our deep neural networks need to learn to encode meaning into sound and then decode it from the sound. And they play this internal game where they do that in a fully unsupervised manner by only listening to sound of the environment, so sounds of spoken language. And we were able to show that the models are very good at learning what we believe is meaningful in human language. They learned words, they learned what we call phonemes. So they learned representations of language that linguists thought are meaningful, which is great because the model, without any explicit instructions, learns what we think is meaningful. Not only that, we were able to show that actually internally they represent sound of language in a very similar way as our human brain represents sounds of language. This is an image of a sound that we play both to humans and then record their brain responses. And we play the same sound to our artificial neural networks. And we've shown that they are extremely similar and that they represent sounds of language and linguistically meaningful properties internally similarly, not only at the abstract level, but also in the pure neural encoding level, right? So you see the red time series is a response to a sound in the artificial neural network. The blue is in the brainstem, and they're very, very similar in a structured way. And I can play you some sounds. So the first sound you'll hear is the sound that we play to both artificial neural networks and human brain. And then the second you'll hear is how this sounds in the brain and then how it sounds in the artificial neural network. So ba, we played this sound. This is in the brain. You can actually hear how the sound sounds in the brain, how electric activity sounds in the brain. And this is how it sounds internally in artificial neural networks. So sperm whales also communicate. And they probably also have some information that they encode in this wonderful, amazing sound system or communication system that we call sperm whale codas. And another whale that is in communication needs to decode that. So we have reasons to believe that this communication is actually meaningful because it happens before hunting, it happens while they're socializing, and so we still don't know what it means, but we have reasons to believe that it is meaningful. It is not, for example, for mating purposes like birds or humpback whale songs, where the function of the song or communication is primarily for mating. Here, it is clearly not. So I'm part of this exciting project called Project SETI that brings together linguistics, biology, machine learning, and scientists from all around the place and around the world into this really noble goal of trying to listen to whales and understand them, what they're saying. So I'm gonna play an example of how two whales are communicating among each other in this communication system that consists of clicks. You can see those beautiful animals, and they have this vast ocean, and we still don't understand well even how the world works. But they communicate and exchange these clicks that we call, so groups of clicks that we call codas. And there are several coda types, and they go back and forth while they're socializing and while they're communicating. So this is one coda, and there's another coda. So there you can have codas with 5 clicks, you can have codas with 10 clicks. And so traditionally, people thought that primarily the number of clicks matters and the timing between them matters, so that those are the main meaningful properties of this communication system, right? So it appeared to be some sort of a Morse code-like communication system, right? But again, we do not know anything that would be meaningful in this communication system. And we don't know if there's something else that might be meaningful, okay? So how did we approach this problem? We took our model that learned language really well, right? So, or our AI model that was built as an artificial baby to learn language from scratch, from raw acoustic data. And we trained it on whales. So instead of human speech, the model learned whale codas, okay? These clicks, groups of clicks that are obviously meaningful in this communication system. And then we looked inside the model and asked it, figuratively speaking, of course, what did you learn? How did you learn to encode information into codas? Where did you encode that information, right? And that is potentially really revealing because whatever network does, it doesn't mean that it's meaningful, but it has a potential to be meaningful. And so before we did this AI experiment, as I mentioned, the Sperm communication system was considered a Morse code-like communication. But our AI model, paired with interpretability technique, suggested that a new dimension might be meaningful as well, in addition to what we thought was meaningful. So then we went and checked, and we went and checked what our model had learned, and we went and checked this new dimension that are called spectral properties, and we found an analogs to human vowels, that these codas are really similar to how we produce vowels. So how do we produce vowels? Okay, this is me saying ah and e. E. Okay, you can probably recognize the voice, and you see the raw sound raw waveform of a recording of me saying ah and e. Now, the way that we say this, the difference between ah and e, is that for ah, we lower the jaw and the tongue, and for e, our tongue is much higher than is the case for ah. And we produce both of them by vibrating our vocal folds, okay? So the main mechanism where vowels are produced is we vibrate vocal folds, and we change our resonant body, our vocal tract. That causes, in the spectrogram or in the spectral representations of our waveform, these bands of frequencies. Okay, so you see for I have two bands that are close together. Those are bands of frequencies called formants. And for I have bands of frequencies that are far apart. And so spectral representations are crucial for distinguishing ah from e. From the raw waveform, it's very difficult to distinguish ah from e. But when you do analysis of the frequencies, you see these formants or bands of shaded bands of frequency forming based on how I articulate, right? So based on the shape of my vocal tract. In a sense, what we're doing is very similar to, say, church organs, where longer tubes in church organs have lower frequency, resonant frequency, and smaller tubes have higher tones, right? So we're familiar with that. So we're flapping our vocal folds and then sending that to our resonant body. Now that looks nothing like sperm whale clicks, right? On the surface, you would think that our vowels, where you have a lot of vocal fold vibration, you see in the vowel, each of these spikes is one vocal fold vibration. So in sperm whales, you would think that that's, there are no parallels between these two. But then we as I mentioned, our AI interpretability technique suggested that this part is meaningful in sperm whales as well. So we went and checked. Now, one thing that we often do in animal research is we're anthropocentric. We look with our human eyes. And I was in this research talk by elephants, and I heard the researcher talking about how elephants have names. And it struck me really hard when I saw that elephants have names and they call each other, but the elephant that is being called replies after 60 seconds or a minute. And that is not how humans converse. So that got me thinking, well, maybe we have timing wrong in these animals, right? So maybe we're too much clouded by our perception of time. And maybe we should change something and we'll see some patterns. So what we did is we take the raw clicks, but remove timing. And that's when patterns start appearing. When you don't remove timing, where the clicks are far from each other, it's very hard to observe patterns. But when you take all the timing away, when you just remove all the white space, we started seeing patterns that are really similar to how humans form vowels. You see here, this is first coda has two peaks, two spectral bands, and then another coda has only one. And so that's how when we basically started removing timing from these clicks, we started seeing really structured patterns that are super similar to how humans form vowels. Remember my A and E, the distinction between my A and E is how that shaded bands of formant frequency form. Well, it turns out that in sperm whales, they do the same. So you see some codas, these are clicks that are grouped into codas, as I mentioned. Some codas have two bands of frequency, and some codas have one. And we saw that over and over again, not only in one whale, but in multiple whales. And you can even hear this when you remove timing, coda, instead of click, 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 they start sounding kind of funny, but you can hear the distinction between coda that we call is of the I vowel type and coda that is of the E vowel type, okay? So A and I, you can actually hear the difference. So it is an audible difference, not so much when you hear to the raw sounds, but when you remove timing, this really becomes apparent. And then we saw other patterns that are beautiful and very interesting as well. So not only can the codas look like vowels and function like vowels in sperm whales, they also have this beautiful trajectory patterns where these bands form shapes, and we have that in language as well. So you see some of the patterns that we call diphthongs, where where sperm whales make these shapes of informant frequencies that are very interesting, again recurrent across whales, and you know, probably, we don't know yet, but likely a candidate for a property that whales encode information into. Now, at the beginning, I show you a conversation between two whales, and for the most part, when we look at these conversations from traditional perspective, when we didn't know about vowels yet, we would think that they're just exchanging the exact same coda type. So this particular family really likes one coda type, which is 1 + 1 + 3. And that sounds like something like click, 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 click. And they exchange that. And before we found these patterns, we thought they're just exchanging the same kind of coda, the same element. But if you look at the vowels now, we see that they're actually exchanging different vowels. So they're exchanging what we call the I vowel and the A vowel in a pattern that we don't fully understand yet, but it seems quite structured. It seems that it's not just random, and it has a potential to encode meaning. So it's possible that they're encoding some meaning into this communication system. So AI model, our artificial baby that we were building in the lab, that learned language really well, and we've shown that it learns language really well, had learned to imitate whales as well, and it had learned to encode information into their sound communication system. Paired with our interpretability technique, where we can now internally look inside the network and ask it, in a sense, what did you learn? So these two things together gave us clues that another dimension is meaningful. And we went and checked it. And we confirmed it with analytical tools. But it is a nice story where AI predicted something that we didn't know yet and helped us find this new discovery. So AI interpretability is not yet an end-to-end system. So it's not the case that you can just take a model and ask it, you know, here's my data I don't understand. Find me new patterns, find me new properties. It's not there yet. It is a tool that helps you find these discoveries, but it has a tremendous potential because these models are more agnostic and in a sense less biased. Of course, they're biased in social ways because they're trained on our data, but they're less biased in observing patterns than perhaps the human researcher. And it's not the case that human researcher is not necessary anymore. Absolutely not. And on the contrary, we need the human researcher more than ever. But we have this new and exciting tool that can help us accelerate discovery. And one exciting thing also is that maybe for the first time in history, AI is so good and we care about animals enough that we have we have these three intelligences that can mutually really inform each other. And today I talked about one case study of that, right? We have the human intelligence that we've known and we've been studied and we've been fascinated by for centuries. We have AI that is becoming so good that it, is becoming a real subject of study, and can help us gain these insights that were not possible before. And we're finally paying enough attention to animals. And we can learn about humans with AI, with artificial models, right? We can learn about artificial models by understanding our brain. We can learn about animals with artificial models. And there are some fundamental questions here. Basically, when we look at all these intelligences together, the questions that have far-reaching consequences. So the question is, are current AI models capable of some human-like intelligence, or will we need some specific? We'll need some extra human? Will we need some extra architectural changes to get to the human level intelligence? And this is, in a sense, a different coin, a different side of the debate, but the same question: is animal communication system a precursor to language? Are animals, do they have all ingredients of human language, just no animal have the same exact language as we have? Or is there something fundamentally uniquely human necessary for language? And in current world of AI, these are really difficult but important questions, because if these models that we have today can scale to a human level intelligence or performance, that is highly consequential. If not, that's also highly consequential, because then we need to find that thing that is uniquely human that allows our intelligence. Okay, so to conclude, I want to say it is super important. It is an exciting time. We have various intelligences now: human, animal, and artificial intelligence. And it is really important that we build models that are like human, that learn more like humans do, but also models that don't learn like humans, so that we have a better understanding of where we're different, where we're similar, animals, humans, and machines. And finally, that together can give us a really useful insight, so that we can use AI to our advantage to make new discoveries, to push the boundaries of science and in general development forward. Thank you for your attention, and I think I can take some questions online, but yes, I think we have some minutes.
Yeah, no, thank you so much, Professor. What an amazing talk. I can imagine that we're going to be hearing a lot from you and also others in this research area in the future. It's extremely exciting. And it's just wonderful to close the conference with something so thought-provoking. So thank you very much for the talk. We are going to move forward, and I really appreciate your time today. Thank you so much.
Thank you.
So we did learn a lot today about really a brave new world. And we hope that the special mix that we offer here in this conference, combining the latest academic thinking with expert and practitioner sessions, left you better informed and both excited and cautioned about the implications of big AI in financial services and fintech, and as we just heard, in many other exciting arenas. I'd like to extend a very hearty thank you to all of our speakers and panelists, and an absolutely huge shout out to Liz Chen, the Fubon Center's Associate Director, without whom this event would certainly not be possible. On behalf of the university and the Fubon Center, I'd like to thank all of you for joining us today. You're now part of a lively and growing fintech ecosystem at Stern. Please follow us on Instagram and LinkedIn to stay in touch and to hear more about our research and about our upcoming events. And for everyone, good luck in your fintech future. Thanks so much.